Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problems 6 to 10 of the AP Calculus AB 012 multiple choice questions. Let's take a look at question number 6. Number 6 reads, a particle moves along the x-axis. The velocity of the particle at time t is 6t minus t squared. What is the total distance traveled by the particle from time t equals 0 to time t equals 3? One tip to keep in mind when calculating the total distance is that when you're calculating the total distance covered, it's independent of direction. Okay? Total distance is basically a scalar quantity. That's why you use the absolute value as opposed to position or displacement that are vector quantities and keep track of the sign. Okay, so let's go ahead and write down the formula for calculating the total distance. The formula is as follows. Formula for total distance is the integral from a to b, basically your time interval, of the absolute value of velocity dt. If we were calculating position or displacement, for example, we wouldn't apply the absolute value. But when you're calculating the total distance, you have to apply the absolute value so that the sign of the distance covered is not considered. You're just calculating the actual distance that the particle travels. Okay? All right, so our velocity function, v of t, is 6t minus t squared. Okay, let's write that again, t squared. Our boundaries, lower limit of integration, a equals 0, upper limit, b equals 3. Now our total distance is going to be the definite integral from 0 to 3 of the absolute value of v of t, which is 6t minus t squared dt. Okay, now anytime you're integrating absolute value functions, you have to take a look at the signs. Okay, you have to make sure that you apply the appropriate signs. So the question is, what is the sign of this function from 0 to 3? In order to determine if there are any sign changes, we have to give ourselves a visual of what the actual graph looks like. Okay, so let's see. If we want to graph this function on the graph v of t, we can simply set the function to 0 and find the zeros. Okay, when you factor out t, from this function, you have t times 6 minus t equals 0. So you're going to have zeros at 0, 0, and if you solve this one for t, you have 6. So 1, 2, 3, 4, 5, 6. So our zeros are 0 and positive 6. Now, since a is negative, this is going to be a downward opening parabola. Okay, so a downward opening parabola with zeros 6 and 0 is going to look something like this. Okay, now what we care about is the sign of this function from 0 to 3. We can see that from 0 to 6 it's positive, so that guarantees that from 0 to 3 this function will attain a positive sign. Okay, we retain a positive sign. So based on this graph, we can simply rewrite this integral as a definite integral from 0 to 3 of 6t minus t squared. There weren't any changes in sign that we have to keep track of. Okay, dt. Now let's apply our power rule in differentiating these two terms. The antiderivative of 6t is 6t squared over 2. Antiderivative of t squared is t to the third over 3. And this has been evaluated from 0 to 3. Now, if we apply FTC Part 1, we'll plug in the upper limit into the antiderivative and subtract it from what you get when you plug in the lower limit. Okay, so when we evaluate the antiderivative at the upper limit, we have 6 times 3 squared over 2 minus 3 to the third over 3. That minus 6 times 0 squared over 2 minus 0 to the third over 3. As you can see, this second component here is going to be 0. So we'll just focus our attention on the left side. Following the order of operations, we have 6 times 9 divided by 2 minus 3 to the third is 27 over 3. So we have 27 over 3. 2 goes here 1, 2 goes here 3 times. 3 times 9 is 27. 27 minus 9, which is what you get when you divide 27 by 3. Your final answer is 18. The answer to problem number 6 is D. All right, let's take a look at question 7. It reads, if y equals the quantity x to the third minus cosine x raised to the fifth power, then y prime equals what? Now, something to recall concerning differentiating composite functions is that when you're differentiating the outer function, you differentiate the outer function evaluated at the inner, and then you multiply that by the derivative of the inner function. Okay, you never differentiate the outer and the inner function and compose them at the same time. Okay, so let's go ahead and write down the formula that reflects what I'm talking about. So the derivative of a composite function, let's say f composed with g of x. Let's say we want to find the derivative of this function is going to be f prime of u multiplied by g prime. So what this is telling us is that when you're differentiating the outer function, you keep the inner function fixed. That's why we're calling it u, to prevent us from differentiating it. Okay, so f prime of u is the derivative of the outer function evaluated at the inner multiplied by the derivative of the inner function. Let's go ahead and apply that formula to this problem. So we have x to the third minus cosine x raised to the fifth power. Now the outer function, let's call it f. F of x is x to the fifth. And the inner function is g of x, which is x to the third minus cosine x. Now let's go ahead and differentiate both. The derivative of f, applying the power rule, is 5x to the fourth power. And the derivative of g, applying the power rule and trig differentiation, we have 3x squared. The derivative of cosine x is negative sign, so this sign would change to positive, plus sine x. So what we're going to do is basically evaluate the derivative of the outer function at the inner. So we'll basically take the inner function g and plug it into the outer function and multiply that by the derivative of the inner function. So y prime is going to be 5. So when we plug in the derivative g into x to the fourth, we have x to the third minus cosine x raised to the fourth power times the derivative of 3x squared plus sine x, the derivative of the inner function. Our answer is option letter E. All right, let's take a look at question 8. It reads, a tank contains 50 liters of oil at time t equals 4. Oil is being pumped into the tank at a rate R of t, where R of t is measured in liters per hour. Selected values of R of t are given in the table above. Using a Riemann sum, write 3 subintervals and the data from the table. What is the approximation of the number of liters of oil that are in the tank at time t equals 15? All right, so one tip to keep in mind concerning finding the amount, which is what we are trying to do here. Finding the number of liters of oil is looking for the amount of oil in the tank at t equals 15. If you're trying to find the amount given rate, what you do is you integrate. Okay, so rate. To find amount given rate, you integrate. All right, there are 2 formulas that are going to guide our problem solving process. Let's go ahead and write them down. Our formulas. The first one is for the right Riemann sum, right rectangle approximation. So right Riemann sum with 3 subintervals, R3, or let's put Rm with 3 rectangles, involves summing up the area of 3 rectangles. So A1 plus A2 plus A3. Now we have 3 rectangles, regardless of if it's midpoint right or left rectangle approximation, you will always have with 1, with 2, and with 3. What changes is the lengths, okay? In a right rectangle approximation, what you do is you pick all the lengths to the right of the left endpoint, okay? So the leftmost length is L1, so we're going to skip that and go straight to L2. So with 1 times length 2 will give us the area of the first rectangle. With 2 times length 3 will give us the area of the second rectangle. And with 3 times length 4 will give us the area of the third rectangle. Okay. Second formula you want to keep in mind is the amount and rate formula. We already talked about this in the tip. If you want to find the amount accumulated by some rate function from time a to b, is going to be the integral from a to b of the rate function, the t, and sometimes you might have an initial amount before you started accumulating the whatever quantity or item that you're accumulating. Okay, in this case, you're accumulating oil. All right, so let's go ahead and apply these formulas to the problem solving process. So we're going to start by figuring out the amount at t equals 15. So if we're looking for the amount at t equals 15, what we're going to be doing is basically looking for the amount that was accumulated in the tank from 0 to 15. Okay? The table, if you examine it, goes from 4 to 15. So with the right rectangular approximation, we can compute the integral from, well, before that, the amount is basically the integral from 4 to 15 of the rate. So the question is, how about from 0 to 4? The problem tells you that at t equals 4 hours, there were 50 liters. So you actually have an initial amount. So we just add on that 15. Okay? So if we want to approximate this exact area using your right Riemann sum, so your right Riemann approximation using 3 rectangles, we just estimate the area from 4 to 15. And we also have to add the 50 liters of oil that was there at time t equals 4. Okay, so t is, the original amount is 50, not 15, so 50. Okay, so now using our formula, the right Riemann approximation is going to be area 1 plus area 2 plus area 3, and let's not forget our 50, the amount of oil in the tank when we started accumulating from 4 to 15. Now let's take a look at the table we have right here. Where are our widths? So just by subtracting the difference in our independent variable, we can figure out our widths. So from 4 to 7, you just subtract, you get width 1, which is 3 units long. And then for the width of the second rectangle, 12 minus 5, width 2 is 5 units wide. And then width 3 of the third rectangle, you just subtract 12 from 15 and you get 3. Now, if you take a look at the output or the rates, we have length 1, length 2, length 3, and length 4. We have too many lengths, okay? So which one are we going to eliminate? Since this is a right Riemann sum, we're going to eliminate the leftmost endpoint. Okay, we're going to consider the lengths to the right of the leftmost endpoint. Okay, so that's what we're going to look at. Now, if we apply that here, we're going to have width 1 times length 2 plus width 2 times length 3 plus width 3 times length 4. You notice length 1 plays no role. If we were doing the left Riemann sum, we'll take this out and we'll consider length 1, 2, and 3. Okay? Alright, so let's go ahead and compute this. We're going to have to do this by hand. Width 1 is 3 times 6.2 plus 5 times 5.9 plus 3 with 3 times 5.6, and then you add 50. When you multiply, you have 18.6 plus 5 times 0.9 is 45, so you have 5 decimal points, you carry over a 4. 5 times 5 is 25, plus the 4 you carried is 29, plus 3 times 6, 18, you put an 8 point, carry a 1, 3 times 5 is 15 plus 1, 16 plus 50. Add all this together, you get the total amount, the approximate total amount in the tank at t equals 15, which is 116.6 liters. So our answer for number 8 is option letter D. Alright, let's take a look at question 9. It says, let f be the function defined above. So we have this function here. For what value of k is the function f continuous at x equals 2? So you want to recall the condition for continuity. A function is continuous if the double-sided limit as x approaches, let's say, an a value is equal to the value of that function at that same a value. Okay, so the left-hand limit is equal to the right-hand limit, the double-sided limit exists, and if that is equal to the value of the function, then the function is continuous. Okay, so continuity just involves left-hand limit equal right-hand limit. Basically, double-sided limit exists equals the value of the function, and you are good to go. So let's use a shortcut for this problem. I don't want to go through the limit finding procedure. I'll just show you a shortcut that works nicely for problems of this nature. Okay, so the procedure is as follows. It's a three-part procedure. Part one, what you do is you substitute the break values, or the break value into the expressions. Okay, substitute the break value into the expressions. And then you equate the expressions. And then lastly, you solve. Okay, so what do I mean by the break? If you take a look at the piecewise defined function we have here, we have a break at x equals 2. So that's the value we're going to substitute. Okay, let's go ahead and do it. So we have the function f of x equals 2x plus 1 times x minus 2 divided by x minus 2 to k, and k at the bottom. And then if you take a look at the function we have above here, well, if we substitute 2, we'll end up with an indeterminate expression, okay, because you have a 0 here times this expression, which is 5 over 0, so that'll be indeterminate. So what we have to do is cancel out this removable discontinuity before we proceed. Okay, so we have that canceled out. So we now have the simplified piecewise defined function 2x plus 1, and then k. This is the value when x is not 2, and then this is the value when x is 2. Okay, we're basically looking for the k value that fills in that removable discontinuity. So based on the procedure, we'll take the break values and substitute for x. So it goes in here. Now for k scenario, this is a constant. So there is nowhere to substitute. That's fine. You don't always have to have somewhere to substitute it in, okay? So we're going to set them equal to each other. 2 times 2 plus 1 equals k. Now this is a double-sided limit, okay? And this is the value of the function. That's what we're doing. So we simplify this, we'll have 2 times 2, which is 4, plus 1 equals k. 4 plus 1 is 5, so we have k equals 5. This is the k value that will cause our function to be continuous. Answer to number 9 is option letter E. All right, let's take a look at number 10. It reads, what is the area of the region in the first quadrant bounded by the graph of y equals e to the x over 2 and the line x equals 2? Now, one tip to keep in mind when it comes to visualizing strange curves, this function right here is an exponential function, okay? It has undergone some kind of dilation, compression in the horizontal dilation in horizontal direction, which is equivalent to a dilation in the vertical direction. So some of you might look at this and you can easily see what the function looks like, but to some of us it might be considered a strange function. When taking the AP exam, you might see some functions that are unfamiliar and you have to carry out calculations on them. Now, in order to make sure that I have my regions properly set up, I need to have an idea as to what this function looks like. So the tip for visualizing functions is that if a function looks strange to you, just make a quick table of values to give yourself a general idea as to what the function looks like, okay? You don't have to make too many values. Look at the problem and determine 3 points or 4 points that can give you an idea as to what the graph looks like. Okay, before we do that, let's write down the formula for finding the area between two curves. So formula for area between two curves. So the area, in this problem, we are configuring ourselves in the vertical direction. Okay, so everything is going to be in terms of x. So if we have a function on the, if we're going in the x direction, we're going to have a function on the top. Okay, and then it will have a function on the bottom. So f top minus f bottom dx. There are no squares here, okay, so be careful. The squares and the pi's have to do with solids of revolution or volume of solids with known cross section. We're just doing area here, so please don't put any squares here. Now, we were talking about creating a graphical representation of the scenario. So let's go ahead and do that. Let's assume that we don't know what y equals x squared looks like. So I'm going to make a table of values. I want to be quick. Remember, we have roughly about 2 minutes for each question on the multiple choice section. So what values am I going to select? I know that I'm in the first quadrant, and I know I'm going to be bounded by this vertical line x equals 2. So I can simply pick 0, 1, and 2. Okay, because the leftmost end will be the y-axis, x is 0 there, and the rightmost end will be this vertical line. So if you put it in 0, what's the output going to look like? You have e to the 0 over 2, which is e to the 0, which is 1. And then we'll plug in 1, we have e to the 1/2, which is the square root of e. If you don't know what the square root of e is, just think about the e, the rational number e. It's roughly 2.7. So the square root is going to be somewhere between 2.7 and 1. You can estimate it to something like 1.6, 1.5. It's somewhere there. Okay, it's not really important that you get the exact value. E to the 2 over 2 is just e to the first power, which is approximately, let's just use 2.7. So the goal is to give ourselves an idea as to what this graph looks like. Okay, and it's going to be an exponential function. So let's say we have the vertical line, x equals 2, right here. And let's graph the points. So we have 0, 1. So let's say this is 1, 2, 3. 0, 1, and then for 1 we have 1.6 somewhere here, and then for 2 we have e, which is 2.7. So you have this nice exponential function right here. Okay, so it's just a general pattern of the function. That's what we're trying to generate. So this is the top function right here, and this will be our bottom function. The top function is the exponential function e to the, I can write this as 1/2 x, and this is 0, your x-axis. Now let's go ahead and apply the formula. The area is going to be the integral from 0 to 2. Remember, our slice is going to be oriented vertically. We're slicing this region in this orientation right here. Okay, so we have dx. Infinite number of slices will give us the exact area when we sum them all up. So f top is e to the 1/2 x. F bottom is 0. So we just integrate these two. So what's the antiderivative of e to the 1/2 x? Just remember that the inner function is a linear function. So if you integrate e to the mx plus b, the antiderivative is simply going to be e to the mx plus b divided by m. Okay, plus c, of course. Now in this case, mx plus b, we have 1/2 x plus 0, so the antiderivative is going to be e to the mx plus b, e to the 1/2 x plus 0 divided by m, which is 1/2. Okay? And then this 0 here is of no consequence. So we're going to evaluate this from 0 all the way to 2. Using FTC part 1, let's simplify this a little bit first. So if I drop change flip, I drop the top and multiply it by the reciprocal of the denominator. I have a 2. Okay. And I can factor out the 2 just to hasten the process. So 2 times e raised to the 1/2 x, evaluated from 0 to 2. So using FTC part 1, I will plug in the upper limit first. So I have e to the 1/2 of 2 minus, plug in the lower limit, e to the 0th power. So that gives us 2 times e to the 1st power minus e to the 0 is just 1. And then when you distribute the 2, you have 2e minus 2. The answer for problem 10 is option letter A. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the AP exam, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to subscribe to our channel for updates to other cool math prep tutorials such as this. If you have any questions or comments, just place it in the comment section below and we'll be more than glad to support you. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.